Welcome to Calculus. We're going to talk about differential equations. Namely, we're going to talk about what we can do with some of the modeling processes that go along with using differential equations. So what I have set up here is a differential equation over here on the left. And then in the middle here is a particular solution to that differential equation. And then over here are some of the constraints that go along with that. And we're going to talk about each of these pieces in a little bit more detail. Just kind of giving you the overview. Now, the background on this particular problem is, let's just say that we have a equation, a function, if you will, that defines the concentration of a particular drug in the bloodstream. And that is what this center equation right here is going to be, is that function that describes that concentration. This differential equation over here, of course, would represent how that concentration is occurring. Now, I picked this problem in particular because it's kind of intuitive. You would expect the concentration of a particular drug to hit your system, spike, and then immediately start to decrease over time. So from that perspective, we would expect this differential equation to have a negative slope, meaning it's constantly decreasing, it's getting smaller. But when we look at the equation on this, it's not so intuitive, which is why this is a really good example to look at. Okay, so now let's talk about a little bit of our constraints here. We have values of K, C sub S, that's an S, not a 5, sorry for the handwriting, and then a value of B. C and S are both positive constants, and B is between 0 and 1 exclusively. So alpha here is a positive number over something between 0 and 1, because we're doing 1 minus B. B is less than 1 but greater than 0, so this value right here is between 0 and 1 in of itself. So alpha is also positive, so it's just a little piece to keep in the back of your head. C sub S would be the initial concentration of the medication. This is the, you take a Tylenol, you're taking 500 milligrams of Tylenol, C sub S is 500 milligrams, that's a constant that's not changing through the rest of this problem. So the concentration in your bloodstream that got hit, that initial hit was 500 milligrams, or whatever the case may be. So the idea here is that we want to verify that this differential equation over here is connected to this particular solution. You have two options. We can separate the variables here on the left-hand side here on this differential equation and show that this integration ends up giving us this function. Or we can take the derivative of this function here and show that it gives us this differential equation. Now, the reason why this is a differential is because it is the change in C over the change in T, and it is made up of the function itself. Here we're actually saying we're having the initial concentration minus the original function right here. Okay, so that's what all this piece is meaning here. So we have a constant divided by t to the b value, b value. Again, so that's just a constant right there. So that'd be our, if you will, this is our constant of variation, and then right here would be the function times that constant of variation. That's what makes this up. So it still has, if you will, it still has a linear approach or linear look to it because we're dealing with a slope. Now, with that said, this function over here is not linear. But remember, we're dealing with differential equations, and we're dealing with individual slopes at individual times, the instantaneous slopes at individual times. So we're dealing with individual slopes which imply a linear relationship, which is part of the reason why we have this conversation of a direct variation for this differential equation. Okay, so if you're wondering where some of those pieces are, that's where they are. So the first thing I'm going to do is I'm going to find C prime, pardon me. Another way we can write that would be D. I could write this as D over dt, and then C sub S, and then 1 minus E to the negative alpha, not infinity, negative alpha t to the 1 minus b power. Right, now keep in mind that 1 minus b is a constant based upon our value for b. Now if you're like, what is the value of b inside this function here? Well, a lot of times we have different constants that have different purposes, and based upon the drugs and the individual person, how big they are, how small they are, these values are going to change. T, of course, would be time here. B is not actually specified in the original problem I'm basing this off of. So we're just going to kind of go with the fact that B is probably based upon gender and or size of the individual. And again, this is not, maybe I should say sex instead of gender. This is talking male, female, because that is really the biological aspect of how these different drugs interact. The levels of your overall body chemistry is going to affect how quickly these chemicals enter and leave your system. Okay, so this DDT is simply talking about finding the derivative of this entire function here. So when we do that, we find C prime here. Another way we could write this is dC over dt, right? So once we found this, that should match up with this original function over there for our differential equation. So this just means d dt means find the derivative of this. C sub s is a constant, so I'm going to treat it like a constant. And then inside here, this is the derivative of 1, which is 0. So I'm going to drop that piece off entirely. And then the derivative of an exponential is the original exponential, right? I'm just going to recopy all that, times the derivative of the exponent. Well, the derivative of the exponent is negative alpha, and then the derivative of we got the exponent there for that t value there, which in this case is just going to be, we're going to have the 1 minus b there, right? And then t to the negative b, because you subtract 1 from the exponent, right? So I multiplied by the exponent, and then I'd subtract 1 from the exponent, and it may seem kind of weird because they're not numbers, so if I put a number with it for a second, maybe this is t to the 5th power. So that'd be 5t to the 4th power, which is taking 1 away from it. Okay, notice also that this is a negative exponent with that b, and b was positive, so we're dealing with a negative exponent, which would eventually move that to the denominator. So that gives us the derivative of that exponent. Now we have a couple pieces that we can kind of play around with here. Notice namely that alpha is k over b, so we can actually rewrite this a little bit. And also notice that we have a negative here and a negative there, which again allows us to be able to do a little bit more rearranging with some of these pieces that might help us down the road, right? So I'm going to have dc over dt is going to be equal to c sub s. Now, negative and negative is a positive. Alpha I can rewrite as k over 1 minus b. I'm going to rearrange things as I go. This gives me 1 minus b, and then I have t to the negative b, and then the original function of e to the negative alpha t 1 minus b, right? So there we go through that. And we notice we have some cancellation right there, and of course we can move that negative to the bottom, so this becomes cs k over t to the b, and then e to the negative alpha t to the 1 minus b, right? So there's that piece. So there is dc dt. Now here is the problem with just doing the derivative. Does this look like the differential equation that was given to us that we were asked to verify? No, it doesn't necessarily look like that right now, but a couple of pieces that we need to pay attention to is that this function, the differential equation up here, has c sub s minus c. Well, we know what c is. C is this function right here that was that very first line. So I can rewrite this as dc dt is also equal to k over t to the b, which I actually have right there, okay, times c sub s, right, minus the original function here, which was c sub s, and I should actually put this in parentheses like this, all right, c sub s, and then 1 minus e to the negative alpha t to the 1 minus b. All right, that's getting a little messy there, so I'll just put a little curly line there. All right, so notice I have a minus sign, and then I'm going to distribute out that c sub s there to there and there, right? I'm going to put it in both places, but I have a minus sign, so that's going to be c sub s minus c sub s, which is going to cancel those out, and then I'm going to have c sub s minus e. I'm going to distribute that out as well, right? So that's going to give me a positive c sub s. So now I have k over t sub b, right, still equal to dc dt. At least I'm hoping these two match up when we're done, right? So I take that negative sign and it makes this one positive. It cancels out the minus, the 1 there. If you need to write that out, pause the video and just kind of prove that to yourself. And then I have c sub s e to the negative alpha T1 minus B, right? Which, if you notice, this piece right here matches that piece down there. So they are, in effect, the exact same thing. Now, some of you may be like, they're not the same thing. Well, no, it's just a matter of rearranging the C sub S with the K and the K over T sub B. And there are different ways you could write this as well. This is not the only one. But now the question becomes, what does this really tell us about the function? Well, let's kind of decipher a few pieces here. I'm going to use green here to kind of point things out. The K is positive, and the K is constant. It's not changing. The B is positive. T is changing, right? T is changing, but this is time, so this is going to be positive. So this whole piece is positive. So that entire first part there is positive, right? Now the thing is as K gets bigger, as T gets bigger, this entire term here is going to 0, because as T gets bigger, you have a positive over a larger and larger positive value. This thing's going to 0, isn't it? But wait a minute though. Hang on. B there is between 0 and 1. So you're really talking about something to like the 1/2 power. What does this do? Well, that's still taking this thing. This is still a constant over something getting bigger and bigger. So, okay, so it's still going to 0, isn't it? All right. Now, C sub S is constant. Alpha here is negative. T is positive, and the power it's being taken to is positive, so this whole piece is positive. So this entire term right here is also going to 0. So what's happening here? This entire thing, the concentration, as time goes on, so as time goes off to infinity, the concentration is going to 0. Now, does it ever get down to complete 0? That's not really the point we're asking here on this one. Really what we're referring to here is, where is it going? As time goes on, the concentration in the bloodstream is going down. It's getting smaller because the slope here is forcing it to do that. So yes, it is a positive slope, but we're getting values where this is going to 0, this piece is going to 0, so 0 times 0 would be going to 0. So this concentration is going to 0. So the concentration is going down as the time is going on. Regardless of where you're starting off with a high concentration, it is going down. Depending on the drug, depending on the individual, it would change, of course. I hope this was useful. I hope this was helpful. If you need additional explanation on this or additional videos on this same topic, please reach out and let me know. Take care.